like what? Chapter 6, momentum and impulse. So what's momentum?
Mass times velocity.
Mass times velocity, yeah, but what is it really? It's really push. You know, when you got some momentum, if a football team has some momentum, they've got some push. If you got some momentum in your life or in school, you got some push. And Newton's third law says that if you push me, what happens? I push back. So you can say push for momentum. You can also say impulse. You can also say impact. So if you got momentum, you got impact. If you got momentum, you can push. And if I push the chart here, what's going to happen? The chart's going to actually push back. So my momentum is equal and opposite the chart's momentum. It's pushing me back. If I got a basketball and bounce a basketball on the ground, as the basketball leaves my hand and hits the ground and then bounces back up to almost the same height, does it lose energy? Does it lose momentum? What happens? What happens in terms, you got to make a distinction between momentum and energy, right? Momentum isn't energy, it's push. It's not joules. It's mass times velocity. So what's happening to the basketball? When the basketball hits the floor, does it transfer any momentum to the floor? And what does the floor do to the basketball? It pushes it back up. So the momentum is transferred to the floor. What about energy? Is energy lost? Momentum's transferred. Is energy lost? If it goes back up to more or less the same height, then what kind of energy is really pretty much the same before and after? Potential. And potential is energy, so if it's this far up to begin with, and it's more or less that far up when it bounces back, it's got the same amount of energy, doesn't it? But what's it done with its momentum? It's transferred its momentum to the floor. The floor has pushed back. Okay, so momentum is just push. Newton's third law, you push me, I push back. So what letter would you use for momentum? Obviously P. What does P stand for? Push. Turns out in physics, if you don't know what letter to give something, you always give it a P. But I like to think of it as push. So, and why is it negative? Because this guy's going to push back. Yes? But it's kind of pesky to put the negative in there, so let's get rid of it. If two objects collide, the initial momentum is going to equal the final momentum. True or false? True, Dan. So, break it down. What's momentum? Andrew said mass times velocity, right? But it's really change in mass times velocity. And since the mass doesn't change, what ends up changing? It's the velocity. So it's really mass, parentheses, V final minus V initial, which you can break down like this. Mass M1 VF minus M1 VI. Final versus initial. Everybody okay with that? Mass doesn't change. M1 V final minus M1 V initial. And then on the other side, we're going to have what? We're going to have M2 V final minus M2 V initial. On both sides, it's just this. It's just M delta V, which breaks down into M VF minus VI. Everybody okay with that? Delta V is just V final minus V initial. Okay. So, the negative's still here. The negative's still here. And we've got a negative on this guy. So watch what happens when you rearrange this. Negative times negative is going to be positive, right? So the M2V1, or the M2VI, is going to be positive. I'm going to leave it right there, M2VI. And this guy over here, M1VI initial for the first object, because we've got two objects, different masses, two objects. I'm going to bring this guy to the right, and he's going to become positive. So I got the initials, M1V1 plus M1VI plus M2VI on the right side. And if I bring this guy over here, I've got, what happened to my VF here? Took this guy over here, made it positive, made that guy positive. This guy's negative, so when I bring him to the left side, it becomes positive. So over here I have M1V final plus M2V final. So this one's a little neater, and that's why they're going to use the formulas. They'll put the finals on one side and the initials on the other, so that you don't have to mess with the negative. So it's cleaner operation, yeah? So, how does this work? Let's say we got two objects, and they're going to collide. And if they're going to collide, they can collide elastically, they can collide inelastically, or they can collide perfectly inelastically. So 3 different ways of collisions, 3 different formulas. So the formulas are all just variations on this. So it's not like you have a whole bunch of different formulas like we saw in Unit 1. Formulas here are pretty straightforward. And they're all just variations on this thing. So let's say we have an object, 5 kilogram object. And let's say it's going 10 meters per second. And it bumps into a second object. Second object is 8 kilograms. And let's say it's going 3 meters per second. So far so good. And they hit each other, boom, and they bounce. So this guy, the first guy, the 5 kilogram object, bounces away with a speed, meters per second, of 5. Can we figure out what the second object, whose mass isn't going to change, can we figure out what the second object is going to move away? Yeah? That's all we have to do, really. We can solve for this guy. So what do we get? 50 plus 24, 74, equals 25 plus 8x. And take away 25 from 74, we're among friends, let's call it 50. 50 equals 8x. 8 goes into 50, we're among friends, 6 times. So this guy's going to move off at roughly 6 meters per second. Is that tough? Okay, so it's an elastic collision. Why? Because all the momentum on the left side is equal to all the momentum on the right side. Now, what happens if we have 2 objects and they hit and stick? Like a pickup truck on the railroad tracks. Train comes along, train hits the pickup truck, and the pickup truck and the train become one. Like this, trailing down the tracks. So what's going to happen now? We're going to go M1, V1, there's a train. M2, V2, there's a truck. What's going to happen over here? They're going to hit and stick. So what happens to the new mass? It's M1 plus M2. We don't need M3 because we just add them up, right? So it's just a new mass, but it's just the sum of the 2 masses. And then we're going to have V3, some new velocity. And this is called hit and stick, or it's called perfectly inelastic. It's a perfectly inelastic collision. True or false, momentum is still conserved. True, momentum is always conserved. Momentum is always conserved. Test question alert. Is momentum always conserved? Yeah, it's always conserved. How about kinetic energy? In this one, in the hit and stick, versus this one, the hit and bounce, this one is an elastic collision. It's a hit and bounce. And kinetic energy is going to be conserved here. But in the hit and stick, perfectly inelastic, then kinetic energy is not going to be conserved. How come a lot of energy is going to be lost to heat and sound and the molecular deformation of the structural components of the objects that are colliding and sticking? Make sense? In other words, potential energy changes in molecular cohesion, stuff like that. Exactly. Okay, so those are the 2 main forms. There's another one for inelastic, when they don't hit and stick, but there's a lot of heat lost. But those are the 2 main ones to worry about. And then the key thing, the key conceptual and the key formula, aside from those, comes down to this. It's called the impulse momentum theory. Impulse momentum theory. And we know momentum is what? M delta V, move. Yeah? MV for move. And if you have impulse, force times the change in time. So if you're fat, what should you do? Obviously move. So there's your impulse momentum theorem right there. In a nutshell. If you're fat, get out and move, baby. So this is force. This is time, mass, and velocity. Are we all good? Okay, this one's interesting. Remember last week when we did work equals FUD? And remember the guy in the ramp versus the guy picking up a box and walking up a ramp versus the guy picking up the box and putting it in the back of the truck right away? They both did the same amount of work, correct? But the guy on the ramp provided less force. How come? Because these two guys were on the same side of the equal sign. Therefore, they had what kind of relationship? Indirect, yeah? So the bigger the distance, the less the force was required to lift an object and put it into a truck. Everybody remember that? Okay, so what about this? Same kind of things going on here. These guys are on the same side of the equal sign, time and force. So therefore, they're going to have what kind of relationship? Inverse. And this is the principle behind seatbelts. So let me give you some historical perspective on this. Back in the day, 1950s, they had cars with metal dashboards. Forget about seatbelts. The dashboards themselves were metal. And if you got into a wreck and you hit your head on the metal dashboard, your head would hit the metal and pop right up. In other words, the time of contact would be real short. And therefore the force of the contact would be real big. So somebody said, well, that's probably not the best design for a car. Let's pad the dash. So late 50s they came up with padded dashes. So now if you hit the dash, your head sank in to the styrofoam and there was longer contact and therefore there was less force and therefore less damage to the cranium. But there's still a lot of hospitalizations as a result. So finally somebody said, okay, let's do what the fighter pilots do and let's put a seatbelt on. When you hit a seatbelt, hit a crash and you got a seatbelt on, your body hits the seatbelt and there's a long time of contact, yes? So what happens to the amount of force? Diminishes appreciably. And then finally they did the strap on over the shoulder, they got the seatbelt on and they got a padded dash, and then they got the airbag. And what does that all do? All those things increase the amount of contact time. So what's the principle? Increase the amount of contact time, decrease the amount of force. And here's one anecdote. You guys remember? You probably don't. Back in the day, Sammy Davis Jr., black dude that used to play in Vegas all the time, used to drive from LA to Vegas in his nice big Cadillac with those big fins. And the marketing geniuses at Cadillac thought, it'd be nice if we had a nice Cadillac with big fins, and on the steering column, let's put a nice green cone to give that Cadillac just the right look. Well, so Sammy's driving down the desert, and he gets into a big crash. No seatbelt, because they didn't have them back in those days. And his left side of his face goes into the cone on the steering wheel. And the cone scrapes out his eye, and the highway patrol sees him sitting next to the tire on the front side of the car with his eye hanging out by a thread. And that was the last time they ever had cones in steering wheels. Physics in action.